So let's talk about 2110 systems and how we manage them. Realistically, what does this all look like in practice? Well, we've already effectively seen the beginnings of a 2110 system because we've said we need PTP. And PTP means we're going to have a grandmaster. We may or may not have a timing reference. We may or may not have some genlock outputs to go to baseband devices, but we're certainly going to then want to connect that up to our network. Also connected up to our network then, we're going to have some video sources. So this could be cameras, could be a media server, various other devices. These are generating ST2110 video streams to transmit over the network. And those are going to be sent to receivers. And a receiver could be a monitor or a multi-viewer, a recorder, or indeed a Brompton Tessera LED processor. Now, we talked earlier about the fact that our network is a packet switched network. And the beauty of this is that we can send multiple video streams over a single connection, over a single cable. So whereas with something like our cameras, there might only be one video signal that we need to transmit down the cable, with something like a media server, we may well want to be able to have multiple video streams simultaneously coming out of that media server. And we can do that over a single network connection, provided there's enough bandwidth there. Even if all of our sources are only transmitting a single video stream each, the other thing that we can do is we can say, well, actually, as a receiver, I want to receive more than one video stream. So a multi-viewer, for example, is obviously going to want to receive multiple video streams. Again, it only needs one connection to the network, and provided it's got sufficient bandwidth, the network is actually going to combine those multiple video streams for us and transmit them down that one cable. So the fact that we're working with a packet switch network is really helpful here. It minimizes the cabling complexity. But we potentially have a lot of video streams flying around here on our network. How do we manage all of this? How do we make sure that the right video stream is getting to the right receiver? Well, there's a few ways that we could go about this, starting with setting all this up manually. And that's a possibility. You can go and configure each device manually, but if you want to do that, you're going to need to set up each device's IP settings. You're going to go and need to configure PTP, not only on the grandmaster, but actually on all of your devices as well. And then for all of your senders and receivers that are using 2110, you're going to go and need to configure those, whether through the front panel or some other management interface, to be able to say, okay, this is the type of 2110 stream I'm trying to create, and this is where I want to send it to. And then on the receiver side of things, okay, which streams am I interested in? What are the properties of those streams? Now, maybe we're going to set all of that up using SDP. That is optional. It certainly makes things a bit easier. But as we mentioned earlier, 2110 does not mandate the exact way in which that should operate. So we can do all of this manually. Typically, however, it may be better to find another way of doing this. Can we use a management protocol which will take care of all of this for us and make our lives easier? Well, we can. And that management protocol is called NMOS. Networked Media Open Specifications. I apologize in advance here for all the acronyms. So this has been developed by AMWA, and it's an open standard that essentially sits on top of 2110 and says, okay, we want to be able to manage all of these devices. And specifically, things we want to be able to do with NMOS. There is a section that talks about registration and discovery. So by registration, we mean if I am a 2110 device with NMOS support, I need to announce my presence onto the network. I need to register the fact that I'm here and I'm running. And then other devices need to be able to discover me. Once everybody knows who is on the network, we then need to worry about, okay, I need to create a connection here between sources and receivers. So there is a section about connection management. There are additional parts to the standard as well to handle things like global system parameters. So things like everybody needs to be set up the same way when it comes to, for example, PTP or perhaps logging. So there is a section of the standard that facilitates that. And there's various other things as well that NMOS gives us. Now, it's important to understand that NMOS is a protocol, not a product. There are products that implement NMOS, both in terms of video senders and video receivers, but also in terms of what we would call a system controller. And an NMOS controller is essentially responsible for finding all the devices that are out there and for setting up those connections. And it might have a user interface. It might be able to say, okay, great, I want to connect this device to that receiver. I want to check that my devices are present and so on. So NMOS itself is the protocol, but then there are products that use NMOS to provide that functionality. What does that look like in terms of extending our system? Well, essentially, we need to add an NMOS controller to our network. And I've drawn it here, connected onto the same, what I'll call a media network, that we are sending all of our video streams over. And that's a perfectly valid way of doing it. But you can also decide to run that management network entirely independently of your media network. And in that case, essentially all of your devices would also be connected to a separate, typically slower and cheaper network, and that simply handles the management. And there are some advantages to doing that. If there is a problem with your main media network, you've inadvertently set something up that has caused some communication problems on that network, well, if you can't use NMOS to then get in and change what your devices are doing, then you're going to have a problem. You're now stuck. Whereas if you are using a separate management network, it's more to set up in the first place, but having done that, you've now got what is essentially an out-of-band connection to all of your devices to be able to go and reconfigure them as you wish, regardless of what your media network is doing, or even if your media network has gone down entirely. Let's talk a little bit about actually what our media network needs to do for us. So the most obvious requirement is it needs to support lots and lots of bandwidth. Video streams, especially when we're talking about 4K and 8K, there is a lot of data there. An 8K video stream can be around 80 gigabits per second, which is a huge amount of video data to have to deal with. Fortunately, there are plenty of network products out there that support that amount of bandwidth, so not a problem for us. We can still use those commercial off-the-shelf switches that we talked about earlier. Now, those switches will typically need to be managed switches. And in fact, it's almost impossible to buy a 100 gig switch that is not a managed switch. And what we mean by managed switch is that essentially an unmanaged switch is going to behave really quite simply in terms of how it routes traffic. It's probably not going to be able to cope with multicast, for example. A managed switch is all about traffic management. So we've got some data that's coming in. What do I have to do to that data? Who do I need to send it to? Who should I not be sending it to? That's all traffic management. That's what we mean when we're talking about a managed switch. On top of that, we need to make sure that the switch is appropriately capable. And there's a range of things we need to look out for here. Things like, is there enough buffer space within the switch for whatever our worst case is going to be in terms of how heavily that switch is loaded up? We need to make sure it's been appropriately configured. So the downside of managed switches is that there are lots and lots of options that you can go in and play with, and it's going to change how that switch reacts in certain situations, how it manages that traffic. And you need to set up things like, what do I want to do with multicast traffic? How am I going to route it? How am I going to handle different devices on the network saying, oh yes, I want to subscribe to that multicast group. I want that video stream, please. All of that needs to be configured within the switch. And you need to think about PTP, you may need to think about things like VLANs. There's a whole host of extra sort of network layer settings that typically need to be configured on a managed switch. So not quite plug and play. At the point where we extend our network, and we may have more than one switch, we also then need to think very carefully about our network architecture. And this is to cover things like how much bandwidth do I need to allow for between two switches? Generally, if I'm working within a single switch, it would be designed to make sure that we can support maximum bandwidth on all of our ports without any problem. But as soon as we split our network into two or more switches, we need to now start thinking about, okay, what traffic flows are we expecting? What streams are going to be running simultaneously between these switches? Do we have enough bandwidth between the switches? Is a single connection between the switches sufficient? Do I need multiple connections? So working out what an appropriate architecture is for a larger network can be quite a complicated topic. And we've already said, well, we expect to have PTP as well. So we need to allow for that. So if we've done all of that, it's just going to work, isn't it? Maybe, maybe not. Why might it not just work? Well, unfortunately, none of these standards are quite like the consumer standards that we have for things like HDMI and DisplayPort. And those standards are intended to be much more plug and play. So unfortunately, AV over IP, not quite so plug and play. And it's not even like SDI, which is a little bit different to HDMI and DisplayPort. So HDMI and DisplayPort, there is essentially a conversation that goes on when you connect up a cable, and the source and the receiver essentially agree what video standard they should be using, what resolutions are supported, what frame rates are supported, and the end result of that should be that the receiver is able to show you a picture. SDI works a bit differently. I kind of call it a blind transmitter. So essentially an SDI source will just decide for itself, this is the video signal I've got, this is what I'm sending. And there is kind of no back channel. So it doesn't matter what's at the other end of the cable. It doesn't actually even matter whether the other end of the cable is connected or not. We're just going to keep transmitting a signal down that cable. And provided the receiver is compatible with the source, okay, great, we're going to be able to show you that video signal. So there are lots of things that we have to set up right if we want an IP system to operate correctly. And we've talked about some of them, not all of them. Unfortunately, it's obviously possible that we get something wrong as part of that configuration. And if that happens, well, it can be quite tricky to figure out what the problem is. And unfortunately, the reality is that a lot of the time you will need specialist technical knowledge and potentially special diagnostic equipment as well to be able to start to work out what's going on. So comparing to something like SDI, if I'm not receiving an SDI signal on my monitor, I can just unplug that cable. Remember, the source is going to keep sending out a signal regardless, and I can try plugging it into a different device. And if it works on a different device, well, there's a good chance that the sender is in fact sending what I'm expecting. Maybe I need to go and check out what's happening on the receiver. IP, because of the extra layers of complexity in terms of the conversations that the devices have with each other and how the network starts to get involved in routing those signals around, it's not quite as straightforward as being able to simply unplug the cable and try it somewhere else. So if it's working, that's great. If it's not working, there are lots of places potentially that you need to go and check whether things are set up right, and that can be tricky. Add to that the fact that we've talked about 2110 and the NMOS standards. But unfortunately, while 2110 essentially says, okay, if you want to do this, this is how you do it. What it doesn't do is say, you must do this thing, and this is how you do it. So it leaves choices. Essentially, it says, you're all grown-ups, so you should make sure that you're trying to do something sensible. If you're not trying to do something sensible, it's probably not going to work. So parts of that standard, and indeed parts of NMOS, are optional. Indeed, in fact, NMOS in its entirety is optional. You can decide not to use NMOS and just use 2110 on its own. But unfortunately, that is going to create some incompatibilities. And even within 2110, we've talked about the fact that certain sender types are not compatible with certain receiver types. So we do have to be grown up about it. We have to be careful about what we're connecting to make sure that this is actually going to work. This is unfortunately compounded by the fact that fairly frequently devices don't actually say up front exactly what their specification is. So what features do they support? What is not supported? So this makes it more difficult to know ahead of time if I'm taking device A and I'm connecting it up to device B. They're both 2110. Is it going to work? Maybe, maybe not. The devil is very much in the details here. Now, this is not an ideal situation, unfortunately, and this has been recognized, fortunately, and is starting to be addressed by additional standards. And that is what we're going to talk about next.